Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Before we begin tonight's gentle journey, feel free to share what time it is and where you're listening from. It's always wonderful to know where these quiet little science stories are drifting off to. Tonight, we're traveling far beyond our familiar solar system to meet a visitor that has journeyed across the vast emptiness between stars. Comet 3I Atlas, the third interstellar object ever discovered, arrived from the cosmic deep carrying secrets about distant worlds and the hidden pathways between them. It's moving faster than any interstellar visitor we've ever seen, larger than its predecessors, and quietly changing how we understand our place in the galaxy. There's no need to follow every detail, just let the gentle current of curiosity carry you wherever it will. So settle in, close your eyes if you like, and let's take a slow, peaceful journey to meet our latest visitor from the stars. On a clear night in July, a telescope in Chile was scanning the star-filled darkness when it spotted something that shouldn't have been there. It was moving. Not like a satellite or airplane, but with the steady, purposeful drift of something far beyond Earth's atmosphere. Something that had traveled unimaginable distances to reach this moment of discovery. The date was July 1st, 2025, and the Atlas telescope in Rio Hurtado, Chile, was performing its nightly routine. Atlas stands for Asteroid Terrestrial Impact Last Alert System, which sounds rather dramatic, but the work itself is quietly methodical. 4 telescopes spread across Chile, South Africa, and Hawaii spend their nights taking pictures of the sky, hundreds of images each evening, looking for anything that moves against the steady backdrop of stars. Picture the dedication required for this work. Each telescope captures around 800 images every night, scanning sections of sky that most people never think to look at twice. The computers process these images, comparing them to previous nights, hunting for the tiny shifts that reveal moving objects. It's like looking for a specific firefly in a field of 10,000 others, except the firefly you're seeking might be from another galaxy entirely. On this particular night, something unusual appeared in the constellation Sagittarius. The object had been given the rather unglamorous designation 11PL3Z, which sounds more like a password than the name of humanity's third confirmed visitor from another star system. But that's how these discoveries often begin, with strings of letters and numbers that hide extraordinary stories. What made this discovery special wasn't immediately obvious. Moving objects appear in telescope images all the time. Most turn out to be asteroids from our own solar system, chunks of rock and ice orbiting our sun in predictable patterns. Others might be comets awakening as they approach the sun's warmth. But when the Minor Planet Center in Cambridge, Massachusetts received the data about 11PL3Z, something about its trajectory caught their attention. The Minor Planet Center is like the cosmic equivalent of air traffic control, tracking and cataloging the thousands of small bodies that populate our solar system. When they ran the calculations for this new object's orbit, the numbers told an astonishing story. The object wasn't following the elliptical path typical of solar system residents. Instead, it was traveling on what astronomers call a hyperbolic orbit, a path so curved and extreme that it could only mean one thing. This visitor had come from somewhere else entirely. A hyperbolic orbit is like a cosmic slingshot trajectory. Instead of circling our sun in a loop, the object swoops in from the depths of space, curves around our star, and then heads back out into the darkness, never to return. It's the calling card of an interstellar wanderer, something that formed around a different star and somehow found its way to our cosmic doorstep. But here's where the story gets even more interesting. As word spread through the astronomical community, researchers began checking their archives. It turned out that 11PL3Z wasn't truly a new discovery at all. The Zwicky Transient Facility in California and the other Atlas telescopes had all captured images of this object before, some dating back to June 14th. It had been there all along, quietly making its way across our sky, waiting for someone to notice it didn't belong. Think about that for a moment. This traveler from another star system had been photographed multiple times by different telescopes, but it took weeks before anyone realized what they were looking at. It's a reminder of how vast and busy our cosmic neighborhood really is, and how easy it might be for visitors to pass by unnoticed. Once astronomers combined all the observational data, the picture became clear. This object had an eccentricity of around 6, which in orbital mechanics terms means it's following an extremely stretched hyperbolic path. For comparison, Earth's orbit has an eccentricity of about 0.017, nearly a perfect circle. Anything with an eccentricity greater than 1 escapes the gravitational pull of what it's orbiting and heads off into space. This visitor was so far beyond that threshold that there was no doubt about its interstellar origins. The discovery of its unusual nature triggered a flurry of follow-up observations. Telescopes around the world turned their attention to this cosmic wanderer, trying to learn as much as possible before it disappeared back into the depths of space. And as more data came in, it became clear that this wasn't just any interstellar visitor. It was something special, something that would challenge our understanding of these rare cosmic messengers. Soon, the object would receive a new designation that reflected its true nature, C 2025, none, marking it as a comet discovered in 2025. But by then, it had already earned a more familiar name among astronomers and space enthusiasts. 3I Atlas, the third confirmed interstellar object to visit our solar system. The first had been Oumuamua in 2017, followed by Borisov in 2019. Now, after 6 years of waiting and watching, we had our third visitor from the stars. As news of the discovery spread, there was a quiet excitement in the astronomical community. Each interstellar visitor teaches us something new about the cosmos beyond our solar system. They're like messages in bottles, carrying information about distant stellar environments and the processes that shape planetary systems across the galaxy. And this new visitor, moving faster and larger than any before it, promised to deliver some particularly intriguing messages indeed. Sometimes the universe delivers exactly what you don't expect, wrapped in ice and moving at breakneck speed. Comet 3I Atlas didn't just announce its arrival, it practically burst through our cosmic front door at a velocity that left astronomers scrambling to keep up. At 58 kilometers per second, this interstellar wanderer is traveling faster than any visitor from beyond our solar system we've ever observed. To put that speed into perspective, imagine something moving the length of nearly 600 football fields every single second. That's fast enough to travel from New York to Los Angeles in about 2.5 minutes. It's a pace that speaks to the incredible forces required to accelerate an object across the vast emptiness between stars and the enormous distances it has already traveled to reach us. This remarkable velocity makes 3I Atlas stand out dramatically from its predecessors. When Oumuamua swept through our solar system in 2017, it was moving at 26 kilometers per second, impressive in its own right. Borisov, discovered in 2019, traveled at 32 kilometers per second. But 3I Atlas is moving nearly twice as fast as Oumuamua and significantly faster than Borisov. It's as if each interstellar visitor is trying to outdo the last in a cosmic speed contest. But speed isn't the only thing that makes this visitor extraordinary. Its orbit tells an equally remarkable story. Astronomers measure orbital shape using something called eccentricity, a number that describes how stretched or circular a path might be. Earth's nearly circular orbit has an eccentricity close to zero. A perfect circle would be exactly zero, while anything greater than 1 means the object is moving fast enough to escape whatever it's orbiting entirely. 3I Atlas has an eccentricity of approximately 6. That's not just hyperbolic, it's extremely hyperbolic, representing one of the most extreme orbital shapes ever measured for any object in our solar system. This suggests that whatever process ejected it from its home system did so with tremendous violence. Perhaps a close gravitational encounter with a massive planet or star that flung it into space with enough energy to carry it across interstellar distances. The comet's impressive size adds another layer to its uniqueness. Early estimates suggest its nucleus is approximately 10 kilometers across, making it substantially larger than both of its interstellar cousins. Oumuamua, with its peculiar elongated shape, measured perhaps a few hundred meters in its longest dimension. Borisov was estimated to be between 1 and 2 kilometers in diameter. 3I Atlas dwarfs them both, an order of magnitude larger than Oumuamua and several times bigger than Borisov. This size difference is significant because larger objects can maintain activity for longer periods and at greater distances from the Sun. As a comet approaches our star, solar radiation heats its surface, causing frozen materials to sublimate directly from solid to gas. This process creates the characteristic coma, a fuzzy atmosphere of dust and gas, and often a tail that points away from the Sun, pushed by solar wind. The larger the comet, the more material it has to work with, and the more dramatic these displays can become. And indeed, 3I Atlas is putting on quite a show. Unlike Oumuamua, which appeared to be a relatively inactive rocky body, this visitor has clearly revealed itself to be a true comet. Observations detected a distinct coma surrounding the nucleus, that telltale fuzzy halo that forms when ice begins to vaporize in the Sun's warmth. This discovery earned the object its official comet designation, C 2025, none, marking it as the first active interstellar comet since Borisov. The comet also sports a tail, though it's relatively modest compared to some of the spectacular displays we see from solar system comets. Initial measurements suggested the tail spans about 3 arcseconds across the sky, appearing at an angle of roughly 280 degrees. That might sound technical, but it translates to a structure extending more than 25,000 kilometers into space, a gossamer ribbon of dust and gas trailing behind the comet as it races toward its closest approach to our Sun. What's particularly intriguing is how the comet's activity level compares to previous interstellar visitors. Borisov was quite active, displaying significant coma growth and a much longer tail that stretched over 140,000 kilometers. Oumuamua showed no clear signs of cometary activity at all, leading to much speculation about its composition and nature. 3I Atlas falls somewhere in between, active enough to clearly be identified as a comet, but not as dramatically so as Borisov. This difference in activity levels tells us something important about the diversity of objects wandering between the stars. Each interstellar visitor represents a sample from a different planetary system, shaped by different conditions and processes. The fact that we're seeing such variety suggests that the galaxy is home to many different types of stellar environments, each contributing its own unique cast-offs to the interstellar population. The brightness of 3I Atlas has also surprised astronomers. It's the brightest interstellar object discovered so far, having increased dramatically in apparent magnitude as it approached the Sun. Between late May and early July, it brightened from magnitude 20 to between 17.7 and 17.8 in the Atlas survey's orange filter. While still far too faint to see with the naked eye, this represents a significant increase in brightness over a relatively short period. This brightening behavior is typical of comets as they approach the Sun and become more active, but the degree of change observed in 3I Atlas suggests it's either larger than initially estimated, more active than expected, or both. The fact that it's the brightest interstellar object we've seen gives astronomers their best opportunity yet to study the composition and behavior of a visitor from another star system. As 3I Atlas continues its journey through our solar system, every observation adds to our understanding of this remarkable visitor. Its extreme velocity, unusual orbit, impressive size, and moderate activity level combine to make it a unique specimen in our small but growing catalogue of interstellar objects. Each new measurement helps refine our picture of what these cosmic wanderers are like and where they might have come from. Picture drawing a map for something that's never been to your neighborhood before and will never return. That's essentially what astronomers face when tracking an interstellar object like 3I Atlas. Unlike the familiar residents of our solar system, which follow predictable orbital patterns year after year, this visitor is making a one-time pass through our cosmic vicinity, following a path determined by forces we can only guess at and origins we may never fully understand. The comet's journey through our solar system follows what mathematicians call an asymptotic trajectory. Imagine throwing a ball past a hill. It approaches from one direction, curves around the obstacle, and heads off in a different direction, never to return to the same path. 3I Atlas is doing something similar on a cosmic scale, approaching our Sun from the direction of the constellation Sagittarius, swinging around our star, and then heading back out into the depths of space. The precision required to map this trajectory is quietly astonishing. Astronomers must account for the gravitational influence of the Sun, the planets, and even smaller bodies like asteroids and comets that might subtly alter the visitor's path. They're essentially solving a celestial mechanics puzzle where the pieces are separated by millions of kilometers, and the solution determines when and where humanity can point its telescopes to catch a glimpse of this rare cosmic guest. As 3I Atlas approaches its closest point to the Sun, called perihelion, it will reach a distance of approximately 1.4 astronomical units on October 30th. An astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers, so the comet will pass just inside the orbit of Mars. This is close enough for the Sun's radiation to significantly warm the comet's surface, likely increasing its activity and making it brighter and easier to study. The comet's path through our solar system reveals the immense speeds involved in interstellar travel. When 3I Atlas reaches perihelion, it won't be slowing down to enjoy the view. Instead, it will whip around the Sun like a cosmic slingshot, using our star's gravity to slightly alter its trajectory before heading back out into the galaxy. The entire visit, from the time it becomes detectable to when it fades from view, spans just a few months in a journey that has likely taken millions of years. What makes tracking this trajectory particularly challenging is that 3I Atlas is moving through a region of space that's relatively crowded with other objects. Our solar system is home to hundreds of thousands of asteroids, thousands of comets, and countless smaller debris. Distinguishing the motion of an interstellar visitor from the orbital dance of solar system residents requires careful analysis and precise measurements over time. The comet's approach from the direction of Sagittarius is particularly significant because this constellation lies along the galactic plane, the bright, disc-shaped region where most of our galaxy's mass is concentrated. Many astronomical surveys avoid this area because the dense star fields can overwhelm sensitive instruments, making it difficult to spot moving objects. The fact that Atlas telescopes can survey this region effectively was crucial to the discovery of 3I Atlas. As the comet continues its journey, it will maintain a safe distance from Earth. At its closest approach to our planet, 3i Atlas will still be approximately 1.6 astronomical units away, or about 240 million kilometers. That's more than 600 times farther than the Moon, ensuring that this visitor poses no threat to Earth while still being close enough for detailed observations. The viewing opportunities for 3i Atlas follow a predictable but limited schedule. From September through early October, the comet should be visible to ground-based telescopes as it approaches perihelion. However, as it swings around the Sun, it will temporarily disappear from view, hidden in the Sun's glare. This is a common challenge when observing comets that pass close to our star. Just when they're becoming most active and interesting, they become impossible to observe safely. But 3i Atlas will make a return appearance. In early December, it will emerge from behind the Sun, visible once again to observers on Earth. This second viewing window will offer another opportunity to study the comet as it moves away from the Sun, potentially revealing how its activity changes as it cools and distances itself from our star's influence. The orbital calculations for 3i Atlas also reveal something profound about the nature of interstellar space. The comet's extreme hyperbolic trajectory suggests it has been traveling through the galaxy for an extraordinarily long time, possibly millions or even tens of millions of years. During this journey, it has been essentially in cold storage, its surface temperature barely above absolute zero, preserving materials from its original stellar system like a cosmic time capsule. This preservation aspect makes interstellar objects particularly valuable to scientists. Unlike comets from our own solar system, which have been repeatedly heated and altered by countless passages near the Sun, interstellar visitors like 3i Atlas may retain relatively pristine samples of materials from their birth environments. They're like archaeological artifacts from distant stellar systems, carrying information about conditions and processes that might be very different from what we see in our own cosmic neighborhood. The trajectory of 3i Atlas also helps astronomers estimate where it might have come from originally. By running the orbital calculations backward, tracing the comet's path through space over millions of years, scientists can identify potential stellar systems that might have been its home. However, the galaxy is a dynamic place, with stars moving in their own orbits around the galactic center, making such backwards tracking increasingly uncertain over long time periods. As 3i Atlas continues its journey through our solar system, every observation helps refine our understanding of its path. The more precisely astronomers can measure its position and velocity, the better they can predict its future course and plan additional observations. It's a race against time, as this visitor will gradually fade from view as it moves away from the Sun and back into the cold darkness between stars. Every photon that bounces off this cosmic wanderer carries a story from another star system. When light from our Sun strikes the surface of 3i Atlas and reflects back toward Earth, it brings with it a wealth of information encoded in ways both subtle and profound. Astronomers have learned to read these messages, extracting details about composition, rotation, size, and activity from the faint glow of an object millions of kilometers away. The global network of telescopes that turned their attention to 3i Atlas represents one of astronomy's quiet marvels. The ability to coordinate observations across continents and time zones, ensuring that this rare visitor remains under constant surveillance as it passes through our solar system. Each observatory contributes its unique capabilities, from specialized filters that isolate specific wavelengths of light to ultra-sensitive detectors that can measure brightness variations smaller than the human eye could ever perceive. The Las Cumbres Observatory telescopes in Hawaii played a particularly important role in unveiling the comet's secrets. These instruments, with their 0.36-meter mirrors, might seem modest compared to the giant telescopes that dominate astronomical headlines, but they're perfectly suited for tracking moving objects over extended periods. Their automated systems can follow a comet across the sky for hours, measuring how its brightness changes with time and revealing the subtle patterns that speak to its rotation and shape. During a carefully planned 1-hour observation sequence, these telescopes captured the gentle rhythms of 3I Atlas as it tumbled through space. Like a cosmic lighthouse with an irregular beam, the comet's brightness rose and fell in a pattern that repeated approximately every 29 hours. This rotational period tells us that the comet is spinning once every 29 hours, a leisurely tumble that's neither particularly fast nor slow by cometary standards. The brightness variations observed during this rotation are remarkably subtle. While some asteroids and comets exhibit dramatic changes in brightness as they spin, revealing highly irregular shapes or surfaces with very different reflective properties, 3I Atlas shows only about 0.2 magnitudes of variation throughout its 29-hour cycle. This suggests either a relatively round shape or a surface with fairly uniform reflective properties, quite different from the dramatic brightness changes observed in Oumuamua. This gentleness in its light curve was actually something of a surprise to astronomers. Oumuamua, the first confirmed interstellar visitor, displayed much more dramatic brightness variations, leading to theories about its highly elongated shape and tumbling motion. The more subdued light curve of 3I Atlas suggests a very different type of object, perhaps more typical of the comets we know from our own solar system. But what truly sets 3I Atlas apart is its brightness overall. This interstellar visitor has the distinction of being the brightest such object ever observed, giving astronomers their best opportunity yet to study the detailed properties of a visitor from another star system. Between late May and early July, the comet underwent a remarkable brightening, increasing from magnitude 20 to between 17.7 and 17.8 in the orange wavelength band used by the Atlas survey. This brightening represents more than just the comet getting closer to the Sun. While proximity certainly plays a role, the increase in brightness also reflects the onset of cometary activity as solar radiation begins to heat the surface and sublimate frozen materials. The timing and degree of this brightening provide clues about the comet's composition and how it responds to our Sun's influence. The orange wavelength band used by Atlas telescopes captures light between 560 and 820 nanometers, a range that includes much of what our eyes would perceive as yellow, orange, and red light. This particular filter choice is practical for detecting moving objects against the stellar background, but it also provides valuable information about the surface properties of objects like 3I Atlas. Amateur astronomers around the world have also contributed to our understanding of this visitor, sharing their observations through platforms like the Astronomer's Telegram. This collaborative approach to astronomy demonstrates how modern communication and technology allow discoveries to be shared and refined in real time, with observers from different locations and time zones adding their pieces to the puzzle. Miguel Alarcón and his colleagues provided particularly valuable measurements of the comet's tail, determining that it extends across more than 25,000 kilometers of space. These observations help constrain models of how much material the comet is losing as it approaches the Sun and provide insights into the processes driving its activity. The images captured by various observers reveal 3I Atlas as a fuzzy, diffuse object quite different from the sharp points of light that represent distant stars. At the center lies the nucleus, the solid heart of the comet, surrounded by the coma, a tenuous atmosphere of dust and gas created by sublimating ice. This combination gives the comet its characteristic appearance and distinguishes it clearly from asteroids, which appear as simple points of light even in powerful telescopes. The tracking shots that follow the comet's motion across the sky create a particularly striking visual effect. Because the camera moves to keep the comet centered in the frame, the background stars appear as streaks of light, while the comet itself remains sharp and detailed. These images capture not just the appearance of 3I Atlas, but also its motion relative to the celestial sphere, a visual reminder that this is truly a visitor from beyond our solar system. As astronomers continue to study the light from 3I Atlas, they're building a detailed portrait of this interstellar wanderer. Each photon carries information about its surface composition, its internal structure, its activity level, and its response to our sun's radiation. Together, these measurements create a scientific biography of an object that has traveled across the galaxy to visit our cosmic neighborhood, carrying with it stories from a stellar system we may never see. Like a detective examining fingerprints, astronomers are learning to read the chemical signatures left by starlight. When light reflects off the surface of 3I Atlas, it doesn't return unchanged. Different materials absorb and reflect different wavelengths, creating a kind of spectroscopic fingerprint that reveals the composition of distant objects. It's a technique that allows scientists to analyze the chemistry of something they'll never be able to touch, based entirely on the quality of light it reflects. The spectroscopic analysis of 3I Atlas reveals a surface that's distinctly reddish compared to our Sun, a characteristic it shares with its interstellar predecessors. This reddish coloration places it in a category similar to D-type asteroids, the dark, primitive objects found primarily in the outer regions of our solar system's asteroid belt. These objects are thought to be rich in organic compounds, and may represent some of the most pristine materials left over from the early solar system. The reddish hue isn't just an aesthetic detail, it's a clue about the comet's history and composition. Objects exposed to cosmic radiation over long periods often develop reddish surfaces as organic compounds are altered by high-energy particles. Since 3I Atlas has likely been traveling through interstellar space for millions of years, this surface coloration might reflect the slow cooking effect of cosmic rays on its outer layers. However, studying the true surface composition of 3I Atlas presents unique challenges. Unlike an inactive asteroid that reflects sunlight directly from its solid surface, this comet is surrounded by an active coma, a diffuse cloud of dust and gas that complicates spectroscopic observations. Much of the light we receive is being scattered by particles in the coma rather than reflected directly from the nucleus, making it difficult to separate the signal from the comet's solid surface from the contribution of its temporary atmosphere. This challenge isn't unique to 3I Atlas. Astronomers faced similar difficulties when studying Borisov, where the brightness of the active coma often overwhelmed the much fainter light reflected directly from the nucleus. It's like trying to study the color of a streetlight while looking through fog. The surrounding material scatters and modifies the light in ways that mask the properties of the source. The coma of 3I Atlas appears as a diffuse, roughly circular glow surrounding the central nucleus in telescope images. This fuzzy halo is created when frozen materials on the comet's surface, primarily water ice, but potentially including other volatile compounds, are heated by solar radiation and sublimate directly from solid to gas. The process is gentle but continuous, creating a tenuous atmosphere that extends for thousands of kilometers around the solid nucleus. Despite its designation as an active comet, 3I Atlas displays only moderate levels of activity compared to some of its cousins. The coma is described as marginal, meaning it's clearly present but not dramatically developed. This suggests either that the comet has a relatively low content of volatile materials or that it hasn't yet been heated sufficiently to drive high levels of sublimation. The comet's tail adds another layer to this picture of modest activity. Initially measuring about 3 arcseconds across the sky, the tail appeared at an angle of approximately 280 degrees, pointing away from the Sun as expected for material being pushed by solar wind. While visually striking in telescope images, this tail is actually quite short compared to what some comets can produce, often getting lost in the brighter glow of the surrounding coma. More detailed measurements by amateur astronomers have revealed that the tail extends over 25,000 kilometers into space, a respectable distance that demonstrates real cometary activity, but falls far short of the spectacular displays produced by some solar system comets. For comparison, Borisov produced a tail stretching over 140,000 kilometers, nearly 6 times longer than what we're seeing from 3I Atlas. This difference in activity levels tells an important story about the diversity of interstellar objects. Borisov was significantly more active, with its coma growing by approximately 1% per day and showing clear signs of sustained material loss over an extended period. The comet had apparently been active for around 100 days before its discovery, suggesting a rich supply of volatile materials responding to solar heating. 3I Atlas, by contrast, appears to be a more restrained performer. While clearly active enough to produce a detectable coma and tail, it's not displaying the dramatic outgassing that characterized Borisov's passage through our solar system. This could reflect differences in composition, internal structure, or simply the amount of volatile material available near the surface. The study of dust production rates provides another window into the comet's behavior. When Borisov was studied in detail during 2020, astronomers determined it was producing dust at a rate of approximately 50 kilograms per second. A substantial output that helped explain how the active coma could overwhelm spectroscopic observations of the nucleus. While similar measurements for 3I Atlas are still being refined, the preliminary observations suggest a more modest rate of material loss. This moderate activity level might actually work in astronomers' favor when it comes to studying the nucleus itself. With less contamination from coma material, there may be better opportunities to observe light reflected directly from the solid surface of the comet, potentially providing clearer insights into its composition and surface properties. The collaborative nature of these observations demonstrates the global effort required to study these rare visitors. Professional observatories, university telescopes, and skilled amateur astronomers are all contributing measurements and images that help build a complete picture of 3I Atlas. The real-time sharing of data through platforms like the Astronomer's Telegram allows discoveries and refinements to be communicated quickly across the international astronomical community. As 3I Atlas continues its approach toward the Sun, its activity levels may change dramatically. Comets often display increasing activity as they get closer to our star, with sublimation rates rising exponentially as surface temperatures increase. The observations made over the coming months will reveal whether this interstellar visitor follows the same patterns as solar system comets or displays unique behaviors that reflect its exotic origins. Every star system is like a cosmic household, and sometimes the neighbors send their leftovers our way. The discovery of 3 distinct interstellar visitors, each with its own personality and characteristics, has opened a window into the diverse environments that exist around other stars. These wandering objects are like cosmic ambassadors, carrying information about planetary formation processes, stellar environments, and gravitational dynamics from across the galaxy. The variety we've observed in just 3 objects is quietly remarkable. Oumuamua appeared to be a dense, rocky body with an unusual elongated shape and no obvious signs of cometary activity. Borisov was clearly an active comet, rich in volatile materials and displaying dramatic outgassing as it approached our Sun. Now 3I Atlas presents yet another variation, a large, moderately active comet that falls somewhere between its predecessors in terms of behavior and composition. This diversity suggests that planetary systems across the galaxy produce a wide range of small bodies, shaped by different formation environments and evolutionary processes. Just as our own solar system contains rocky asteroids, icy comets, and everything in between, other stellar systems appear to generate their own unique populations of small objects. The fact that we're seeing such variety in just 3 examples hints at the rich complexity that likely exists in the broader galactic population. The process of planetary system formation appears to be both universal and highly variable. All stellar systems begin with a disk of gas and dust surrounding a young star, but the details of how that material condenses into planets, asteroids, and comets can vary dramatically depending on the star's mass, the disk's composition, and the presence of nearby stellar companions. These differences in formation history are preserved in the small bodies that eventually get ejected into interstellar space. Consider the implications of Borisov's unusual composition. This comet showed high concentrations of carbon monoxide relative to water, a chemical signature that's uncommon among comets in our solar system. This suggests it formed in an environment where carbon monoxide could condense and be incorporated into solid bodies, likely a colder region than where most of our solar system's comets originated. Such conditions might be typical around red dwarf stars, which are cooler than our Sun and represent the most common type of star in the galaxy. The size distribution of interstellar objects also tells an interesting story. 3I Atlas, at approximately 10 kilometers across, is significantly larger than its predecessors. If this size difference reflects real variation in the interstellar population rather than just observational selection effects, it suggests that some stellar systems are capable of ejecting quite substantial objects. The gravitational processes required to accelerate a 10-kilometer object to interstellar speeds are correspondingly more energetic than those needed for smaller bodies. The orbital characteristics of these visitors provide clues about the ejection mechanisms that sent them on their interstellar journeys. The extreme hyperbolic orbit of 3I Atlas, with its eccentricity of 6, indicates a particularly violent ejection event. Such high velocities typically result from close gravitational encounters with massive objects, perhaps gas giant planets or stellar companions in binary star systems. The rarity of these detections also constrains our understanding of how common interstellar objects might be. The Atlas survey has been scanning the sky for several years and has found only one confirmed interstellar object during that time, leading to estimates of about 0.001 objects per cubic astronomical unit of space. This suggests that while such objects are certainly present throughout the galaxy, they're not overwhelmingly common, at least not in the size range that current surveys can detect. However, this apparent rarity might be misleading. Smaller interstellar objects, perhaps only a few meters or tens of meters across, could be passing through our solar system regularly without being detected by current surveys. The same might be true for objects that follow trajectories that don't bring them close enough to the Sun to become easily visible. We may be seeing only the tip of a much larger population of interstellar wanderers. The chemical diversity observed in interstellar objects also provides insights into the variety of stellar environments across the galaxy. Different types of stars create different conditions in their surrounding planetary disks, influencing what types of materials can condense and how planetary formation proceeds. Red dwarf stars, which make up about 75% of all stars, create cooler environments that might preserve more volatile materials. Massive stars burn brighter and hotter, potentially creating very different chemical environments in their planetary systems. The study of interstellar objects is still in its infancy, but already these few examples are reshaping our understanding of planetary system formation and evolution. Each visitor carries isotopic signatures, chemical compositions, and structural characteristics that reflect the conditions in its birth environment. By studying these cosmic travelers, astronomers are essentially conducting a survey of stellar environments across the galaxy without having to travel to distant star systems. The gravitational dynamics that create interstellar objects also tell us about the evolutionary history of planetary systems. Our own solar system likely went through a period of gravitational instability early in its history, when the giant planets migrated from their original positions and scattered smaller bodies throughout the system. Some of these objects were ejected entirely, becoming our contribution to the galactic population of interstellar wanderers. The fact that we're detecting interstellar objects at all suggests that this ejection process is common across many types of stellar systems. Planetary formation appears to be an inherently messy process, generating not just stable planetary architectures, but also substantial populations of leftover material that gets flung into space. These cosmic castaways then spend millions or billions of years drifting through the galaxy before occasionally encountering other stellar systems. As our detection capabilities improve and more interstellar objects are discovered, we'll begin to build a more complete picture of this galactic ecosystem. Each new visitor will add to our understanding of stellar environments, planetary formation processes, and the complex gravitational dynamics that shape solar systems across the galaxy. These rare cosmic encounters are teaching us that our solar system is part of a vast, interconnected network of stellar environments, each contributing its own unique objects to the wandering population that fills the spaces between the stars. Not every planet gets to stay home forever, and sometimes entire chunks of worlds get shown the cosmic door. The violent gravitational processes that can fling objects out of star systems represent some of the most dramatic events in planetary system evolution, capable of accelerating mountain-sized objects to speeds that carry them across the galaxy. Understanding these ejection mechanisms helps explain how interstellar wanderers like 3I Atlas came to be drifting through the cosmos in the first place. The story begins with the chaotic early days of planetary system formation. Picture a young star surrounded by a disk of gas, dust, and countless small bodies, all gradually condensing and colliding to form the building blocks of planets. It's not a gentle process. Gravitational interactions send objects careening through space, sometimes toward the growing star, sometimes toward the outer reaches of the system, and occasionally, with just the right combination of speed and trajectory, entirely out of the system altogether. Close encounters with giant planets represent one of the most efficient ways to achieve interstellar escape velocities. Imagine a small body, perhaps a comet or asteroid, following a stable orbit in the outer regions of a star system. If a massive planet migrates inward or outward due to gravitational interactions with other planets, it can disrupt the orbits of countless smaller objects. Some get captured into new orbits, others are sent spiraling into the star, but a fortunate few receive gravitational kicks strong enough to send them racing toward interstellar space. The mathematics of these encounters are elegantly brutal. A small object passing close to a massive planet can gain tremendous velocity through what's called a gravitational slingshot effect. The planet's gravity accelerates the object as it approaches, and if the geometry is just right, the object can steal enough orbital energy from the planet to exceed the escape velocity of the entire star system. Its cosmic pool, played with objects the size of mountains and forces measured in planetary masses, Our own solar system provides examples of how such processes might work. During its early history, the giant planets likely migrated significantly from their original positions. Jupiter may have moved inward toward the Sun before being pulled back outward by gravitational interactions with Saturn. This grand reshuffling, sometimes called the grand tack model, would have scattered enormous numbers of small bodies throughout the solar system, ejecting many of them entirely. The Late Heavy Bombardment, a period roughly 4 billion years ago when the inner solar system experienced intense impacts, might represent evidence of this same process. As the giant planets settled into their current configurations, they scattered leftover planetesimals throughout the system. Some struck the inner planets, creating the heavily cratered surfaces we still see on the Moon and Mercury, while others were flung outward into the Kuiper belt or beyond. Binary star systems present even more dramatic opportunities for gravitational ejection. When two stars orbit each other, their combined gravitational field creates a complex environment where small bodies can experience extreme accelerations. Objects passing between the two stars or around their combined system can receive gravitational kicks that send them flying at tremendous speeds. Some computer simulations suggest that binary systems might be particularly efficient at producing high-velocity interstellar objects. The ejection process isn't limited to small bodies. In some cases, entire planets can be ejected from their birth systems. These rogue planets, unbound from any star, may represent a significant population wandering through the galaxy. Some estimates suggest there might be as many free-floating planets as there are stars, a vast population of worlds drifting alone through the cosmic dark. The velocity distribution of ejected objects depends strongly on the ejection mechanism. Gentle perturbations might send objects into interstellar space at relatively modest speeds, while close encounters with massive planets or passage through binary star systems can produce much higher velocities. The 58 km per second speed of 3I Atlas suggests a particularly energetic ejection event, perhaps involving a close encounter with a massive planet or passage through a complex gravitational environment. Stellar encounters can also trigger ejection events. When stars pass relatively close to each other, their gravitational fields can disrupt the outer regions of each other's planetary systems. Objects in distant orbits around one star might be torn away and captured by the other, or sent flying into interstellar space entirely. In dense stellar environments like globular clusters or the galactic center, such encounters might be relatively common. The composition and structure of ejected objects carry information about where in their original system they formed. Objects from the inner regions of a stellar system might be rocky and depleted in volatile materials, having formed in the warm environment close to their star. Those from the outer regions are more likely to be ice-rich and preserve volatile compounds that condensed in the cold outer reaches of their birth system. 3I Atlas, with its large size and moderate activity level, likely formed in the outer regions of its home system, where water and other volatile materials could condense into solid form. Its subsequent ejection required enough energy to accelerate a 10-kilometer object to interstellar speeds, suggesting a particularly dramatic gravitational encounter. The precise mechanism remains a mystery, but the object itself serves as evidence that such violent events do occur in stellar systems across the galaxy. The timing of ejection events also matters for the object's subsequent evolution. Objects ejected early in their system's history might preserve very primitive materials from the original protoplanetary disk. Those ejected later might show signs of thermal processing, chemical alteration, or impact modification from their time in their birth system. By studying the composition and structure of interstellar objects, astronomers can piece together not just where they came from, but when they were ejected and what their home systems were like during different phases of evolution. As we continue to discover and study interstellar objects, we're building a picture of the galactic recycling process that connects all stellar systems. Every star system likely both produces and receives interstellar wanderers, creating a vast network of material exchange across the galaxy. These ejection processes, violent and dramatic as they might be, represent one of the ways that stellar systems communicate with each other across the vast distances of interstellar space. Finding an interstellar visitor is like spotting a particular grain of sand while it's flying past your window. The challenge isn't just that these objects are small and faint, it's that they're moving against a background of hundreds of thousands of other moving objects, most of which follow predictable patterns that astronomers have mapped and catalogued over decades. Distinguishing an interstellar interloper from the familiar residents of our solar system requires patience, precision, and more than a little bit of luck. The Atlas survey that discovered 3I Atlas represents a masterpiece of systematic sky monitoring. Each night, 4 telescopes spread across 3 continents take hundreds of images of different patches of sky, looking for anything that has moved since the previous night's observations. It sounds straightforward in principle, but the practical challenges are enormous. The sky is vast, the objects are faint, and the data requirements are staggering. Consider the scale of this undertaking. Each Atlas telescope captures around 800 images per night, and with 4 telescopes operating, that's over 3,000 images captured every single night, weather permitting. Each image must be compared with previous observations of the same region, a process that requires sophisticated software to identify and track moving objects while filtering out false detections caused by cosmic rays, satellite trails, and electronic noise. The software that processes these images has been trained to recognize the movement patterns typical of solar system objects. Asteroids in the main belt between Mars and Jupiter follow relatively predictable paths. Near-Earth asteroids have their own characteristic motions. Comets approaching from the outer solar system display yet another pattern of movement. But an interstellar object moves differently, following a trajectory that doesn't fit the familiar categories. This is where the challenge becomes particularly acute. The automated systems that process survey data are designed to flag unusual objects for human review, but they must balance sensitivity against the flood of false alarms that would overwhelm astronomers if the criteria were too broad. An interstellar object might be flagged for unusual motion, but so might a near-Earth asteroid on an eccentric orbit, a comet making its first approach to the inner solar system, or even a piece of space debris following an unusual trajectory. The discovery of 3I Atlas illustrates both the power and the limitations of current detection methods. The object was actually photographed multiple times by different telescopes over several weeks before anyone realized what it was. The Zwicky Transient Facility in California and 3 Atlas telescopes had all captured images of the object dating back to June 14th. But it wasn't until the July 1st observation that the pieces came together and its interstellar nature was recognized. This delay highlights one of the fundamental challenges in interstellar object detection, the need for enough observations to establish a reliable orbit. A single image shows only position, while 2 images reveal motion. But determining whether that motion represents an interstellar trajectory requires multiple observations spread over time, allowing astronomers to calculate the object's path with sufficient precision to distinguish between solar system and interstellar origins. The timing of these discoveries is often critical. Interstellar objects typically become detectable only when they're close enough to the Sun for solar heating to brighten them, or, in the case of inactive objects like Oumuamua, when they're close enough for reflected sunlight to make them visible to sensitive instruments. By the time they're discovered, they're already on their way out of the solar system, leaving limited time for detailed study. This time pressure creates a cascade of challenges for the astronomical community. Once an interstellar object is confirmed, observatories around the world must quickly coordinate to maximize the scientific return from this rare opportunity. Telescopes must be scheduled, instruments configured, and observing programs modified, all while the object continues its relentless journey toward the outer solar system and eventual invisibility. The galactic plane presents particular challenges for interstellar object detection. This region, where most of our galaxy's stars are concentrated, is often avoided by astronomical surveys because the dense star fields can overwhelm sensitive instruments. However, the direction from which 3I Atlas approached, through the constellation Sagittarius, lies directly along the galactic plane. The ability of Atlas telescopes to survey this region effectively was crucial to the discovery. Size bias represents another significant limitation in current detection capabilities. All three confirmed interstellar objects are relatively large by small body standards, ranging from hundreds of meters to several kilometers across. Smaller interstellar objects, perhaps only tens of meters in diameter, almost certainly pass through our solar system undetected. These objects would be too faint to spot until they're very close to the Sun, if they can be detected at all with current technology. The orbital bias in our detections is equally significant. Objects that pass close to the Sun become brighter and more easily detectable, but those following trajectories that keep them in the outer solar system might remain invisible throughout their entire passage. We're essentially seeing only interstellar objects that happen to come close enough to our star to become detectable, potentially missing entire populations that follow different types of trajectories. Weather and seasonal constraints add another layer of complexity to interstellar object detection and follow-up. Ground-based telescopes are limited by local weather conditions, and objects that happen to be visible only during poor weather at multiple observatory sites can be lost entirely. The seasonal visibility from different locations on Earth also affects how long an object can be observed and by which telescopes. Despite these challenges, the detection rate for interstellar objects appears to be increasing. This partly reflects improvements in survey sensitivity and coverage, but it might also indicate that we're beginning to sample the true population of these cosmic wanderers. As next-generation surveys come online, with even greater sensitivity and sky coverage, the trickle of interstellar discoveries may become a steady stream. The serendipitous nature of many astronomical discoveries means that some of the most important interstellar objects might be found by surveys designed for entirely different purposes. The same wide-field telescopes used to search for supernovae, monitor variable stars, or track near-Earth asteroids are equally capable of spotting interstellar visitors, provided their data is analyzed with the right techniques and sufficient care. As detection methods improve and more interstellar objects are discovered, astronomers are developing better strategies for rapid response and coordinated follow-up observations. The goal is to maximize the scientific return from each rare visitor while building a statistical understanding of the broader population of objects wandering between the stars. Each interstellar visitor carries a passport stamped with the chemistry of its birthplace. The atoms and molecules that make up these cosmic wanderers were forged in the nuclear furnaces of distant stars, condensed in the cold outer regions of alien planetary systems, and shaped by billions of years of cosmic radiation during their journey through interstellar space. By analyzing their composition, astronomers are essentially reading chemical love letters from stellar systems we may never visit. The spectroscopic fingerprints of interstellar objects tell stories about environments that might be wildly different from anything in our solar system. When starlight reflects off the surface of 3I Atlas, it carries information encoded in the precise wavelengths of light that are absorbed and reflected by different materials. Each chemical element and compound has its own unique signature, like a molecular barcode that reveals its presence even across millions of kilometers of space. Borisov's remarkable chemical composition provides perhaps the clearest example of how alien these environments can be. This interstellar comet showed unusually high concentrations of carbon monoxide relative to water, a ratio that's quite different from what we typically see in comets from our own solar system. This chemical signature suggests that Borisov formed in an environment cold enough for carbon monoxide to condense into solid form and be incorporated into the growing comet. Such conditions might be typical around red dwarf stars, which burn much cooler and dimmer than our Sun. Red dwarfs represent about 75% of all stars in the galaxy, making them the most common stellar environments. If Borisov originated from such a system, it would represent our first direct sample of materials from the most typical type of stellar environment in the galaxy, a cosmic environment quite different from the relatively warm and bright system we call home. The isotopic ratios preserved in interstellar objects provide even more detailed information about their origins. Isotopes are versions of the same element with different numbers of neutrons, and their relative abundances can reveal details about the nuclear processes that created them. Different types of stars produce different isotopic signatures, and by measuring these ratios in interstellar objects, astronomers can potentially identify what type of star system they came from. The preservation of these chemical signatures depends on the interstellar journey itself. During their million-year or longer voyages through space, these objects are bombarded by cosmic radiation, high-energy particles that can gradually alter their surface composition. This cosmic weathering process tends to redden surfaces and can create new chemical compounds, but it typically affects only the outermost layers of material. The reddish color observed in all three confirmed interstellar objects might partly reflect this cosmic weathering process. Organic compounds exposed to cosmic radiation over long periods tend to develop reddish coloration as their molecular structure is altered by high-energy particles. This means that the surfaces we observe might not perfectly represent the original composition of these objects, adding another layer of complexity to their interpretation. However, the interiors of these objects likely remain largely unaltered by their interstellar journey. If we could drill into the heart of 3I Atlas or any other interstellar visitor, we might find materials that preserve the original chemistry of their birth environment with remarkable fidelity. The challenge is accessing these pristine interiors through remote observations alone. Cometary activity provides one window into interior composition. As solar heating sublimates ice from below the surface, it carries with it dust and gas that originated deeper within the object. The composition of this outgassed material can reveal information about the bulk chemistry of the comet, not just its weathered surface layers. This is why active comets like Borisov and 3I Atlas are potentially more informative than inactive objects like Oumuamua. The moderate activity level of 3I Atlas might actually work in astronomers' favor when it comes to studying its composition. Unlike Borisov, whose dramatic outgassing created a bright coma that overwhelmed spectroscopic observations of the nucleus, the gentler activity of 3I Atlas might allow better access to signals from the solid surface while still providing samples of interior material through its modest outgassing. The dust-to-gas ratio in cometary outgassing also provides clues about formation, environment, and composition. Different stellar environments might produce comets with very different mixtures of rocky and icy materials. A comet that formed in a debris-rich environment might have a higher dust content, while one that condensed in a relatively clean region of a protoplanetary disk might be more purely icy. The seasonal effects that many solar system comets display provide another window into composition and structure. As different regions of a comet's surface are exposed to solar radiation during its rotation and orbital motion, the composition of outgassed material can change, revealing the heterogeneous nature of the object. Whether interstellar comets like 3I Atlas display similar seasonal variations could reveal whether they formed through similar processes as solar system comets. The size and density of interstellar objects also constrain their likely composition and formation environment. 3I Atlas, at approximately 10 kilometers across, represents a substantial object that would have required specific conditions to form and survive ejection from its birth system. The processes that create such large objects in the outer regions of planetary systems might be different from those that produce smaller bodies. Volatile content represents perhaps the most sensitive indicator of formation environment. Different stellar systems might preserve different types of ices depending on their thermal history and the composition of their original protoplanetary disks. Water ice is common throughout the galaxy, but more exotic ices like solid nitrogen, carbon monoxide, or methane might be preserved only in the coldest environments around the faintest stars. The trace element composition of interstellar objects could potentially reveal details about the supernova explosions that enriched their birth systems with heavy elements. Different types of supernovae produce different patterns of element abundances, and these signatures might be preserved in objects formed from the enriched material. By studying the detailed composition of interstellar visitors, astronomers might be able to trace their origins back to specific types of stellar environments and nucleosynthetic processes. As analytical techniques improve and more interstellar objects are discovered, we're beginning to build a library of compositions that represents a survey of stellar environments across the galaxy. Each new visitor adds another data point to our understanding of how planetary systems form and evolve around different types of stars, providing ground truth for theoretical models of planetary formation that have previously relied entirely on observations of our own solar system. 3 visitors don't make a pattern, but they're starting to sketch the outline of something bigger. With Oumuamua, Borisov, and now 3I Atlas, astronomers have their first glimpse of what the population of interstellar objects might look like. Each discovery has been unique, presenting characteristics that challenge assumptions and expand our understanding of what these cosmic wanderers can be. But taken together, they're beginning to reveal patterns that speak to fundamental processes operating throughout the galaxy. The size progression is perhaps the most immediately striking pattern. Oumuamua, the first discovered, was relatively small, perhaps a few hundred meters in its longest dimension. Borisov was larger, estimated at 1 to 2 kilometers across. 3I Atlas dwarfs both of its predecessors at approximately 10 kilometers in diameter. This progression might be coincidental, or it might reflect the increasing sensitivity of detection systems and our growing ability to spot larger objects at greater distances. But the size differences also raise intriguing questions about the processes that create and eject interstellar objects. Larger objects require more energy to accelerate to interstellar speeds, suggesting that some stellar systems are capable of much more violent ejection events than others. The 10-kilometer scale of 3I Atlas implies gravitational interactions with very massive objects, perhaps multiple gas giant planets or close encounters with stellar companions. The activity levels of these 3 objects tell another part of the story. Oumuamua showed no clear signs of cometary activity, appearing more like a dense, rocky asteroid than an ice-rich comet. Borisov was dramatically active, with extensive outgassing and a long, prominent tail. 3I Atlas falls between these extremes, clearly active but more restrained than Borisov. This range suggests that interstellar space contains both volatile-rich and volatile-poor objects, reflecting different formation environments and histories. The compositional diversity revealed by these three objects hints at the variety of stellar environments across the galaxy. Oumuamua's apparent lack of volatile materials might indicate formation in a warm environment close to its parent star, or perhaps extensive processing that removed any ice originally present. Borisov's unusual chemistry, rich in carbon monoxide, suggests formation in a cold environment, possibly around a red dwarf star. 3I Atlas, with its moderate activity and substantial size, might represent formation in an environment more similar to the outer regions of our own solar system. The velocity distribution of these interstellar visitors provides clues about the ejection mechanisms that sent them on their journeys. Oumuamua's 26 km per second, Borisov's 32 km per second, and 3I Atlas's 58 km per second represent a wide range of ejection velocities. The extreme speed of 3I Atlas suggests a particularly violent ejection event, while the more modest velocities of the other two might reflect gentler gravitational perturbations. Statistical analysis of these three discoveries has allowed astronomers to make preliminary estimates of the density of interstellar objects in space. The current estimate of approximately 0.001 objects per cubic astronomical unit is based primarily on the detection rate of the Atlas survey, which has been systematically monitoring the sky for several years. This density is lower than some earlier estimates, but still suggests a substantial population of objects wandering between the stars. However, these statistical estimates come with enormous uncertainties. The sample size of three objects is vanishingly small for making robust statistical inferences, and each discovery could be an outlier rather than a representative sample. The detection biases inherent in current surveys also complicate these estimates. We can only detect objects that become bright enough to spot, which typically means they must pass relatively close to the Sun. Objects following trajectories that keep them in the outer solar system might remain completely invisible. The size bias in our detections is particularly significant. All three confirmed interstellar objects are relatively large by small body standards. Smaller objects, perhaps only tens of meters across, almost certainly pass through our solar system regularly, but remain below the detection threshold of current surveys. The true population of interstellar objects might be dominated by these smaller bodies that we simply cannot see. The orbital characteristics of the three discovered objects also show interesting patterns. All follow hyperbolic trajectories, as expected for interstellar visitors, but their eccentricities vary significantly. Oumuamua had an eccentricity of about 1.2, Borisov about 3.4, and 3I Atlas approximately 6. These differences reflect the varying amounts of energy involved in their ejection from their home systems and their subsequent gravitational interactions with our solar system. The approach directions of these objects provide another piece of the puzzle. They haven't all come from the same direction in space, which is reassuring evidence that they represent independent discoveries rather than fragments of a single disrupted body. The distribution of approach directions might eventually reveal something about the local structure of the galaxy and the distribution of nearby stellar systems that could serve as sources for these wanderers. Temporal patterns in the discovery rate are beginning to emerge as well. Oumuamua was discovered in 2017, Borisov in 2019, and 3I Atlas in 2025. This roughly 3-year spacing might be coincidental, or it might reflect the typical interval between objects large enough to be detected by current surveys. As survey sensitivity improves, this discovery rate might increase dramatically. The seasonal timing of discoveries also shows some clustering. All three objects were discovered during periods when they were becoming brighter as they approached the Sun, which makes sense given the sensitivity limitations of current surveys. But this observational bias means we might be missing objects that follow trajectories, keeping them faint throughout their passage through the inner solar system. The follow-up observation campaigns triggered by each discovery have revealed the importance of rapid response in studying these fleeting visitors. The limited time available for detailed study has pushed the astronomical community to develop new protocols for coordinating international observations and maximizing the scientific return from each rare encounter. As the sample size grows beyond 3 objects, astronomers will be able to draw more robust conclusions about the population characteristics of interstellar visitors. The patterns that are only beginning to emerge with 3 objects will become clearer with dozens or hundreds of examples. Future discoveries will reveal whether the trends we're seeing are real or simply artifacts of small number statistics and observational biases. The diversity already apparent in just 3 objects suggests that the population of interstellar wanderers is rich and varied, reflecting the complex processes that shape planetary systems throughout the galaxy. Each new discovery will add another piece to this cosmic puzzle, gradually revealing the nature of the vast population of objects that wander eternally between the stars. Engineers and dreamers are already sketching plans to catch up with these ancient travelers. The prospect of sending a spacecraft to intercept an interstellar object represents one of the most technically challenging missions ever conceived, requiring speeds and precision that push the boundaries of current technology. Yet the scientific payoff would be extraordinary. The first close-up study of pristine materials from another star system, potentially answering fundamental questions about planetary formation and the distribution of life-building materials throughout the galaxy. The primary challenge is speed. 3I Atlas is racing through our solar system at 58 kilometers per second, fast enough to cross the entire United States in about 2.5 minutes. By the time such an object is discovered and confirmed as interstellar, it's typically already on its way out of the solar system, leaving precious little time to plan, build, and launch an interceptor mission. The window of opportunity is measured in months, or at most a few years, far shorter than the typical decade required to design and build a planetary mission. Current chemical propulsion technology simply cannot achieve the velocities needed to catch up with fast-moving interstellar objects. The fastest spacecraft humans have ever built, like the Parker Solar Probe, can reach speeds of around 200 kilometers per second when using the Sun's gravity for assistance. While impressive, this is still slower than many interstellar visitors, and achieving such speeds requires carefully planned trajectories that take years to execute. Nuclear propulsion represents one potential solution to this speed challenge. Concepts like nuclear pulse propulsion, where a spacecraft is pushed forward by a series of small nuclear explosions, could theoretically achieve the velocities needed to intercept interstellar objects. However, such technologies remain largely theoretical and would require years of development and testing before they could be ready for actual missions. Solar sails offer another intriguing possibility. These ultra-lightweight spacecraft use the pressure of sunlight for propulsion, gradually accelerating to high speeds over long periods. A solar sail mission to intercept an interstellar object would require advance warning of the object's approach, allowing time for the spacecraft to build up the necessary velocity. Recent proposals have suggested that with sufficient lead time, solar sail technology might be able to reach some interstellar visitors. The advance warning problem represents perhaps the greatest obstacle to intercept missions. Most interstellar objects are discovered only when they're already close to the Sun and becoming bright enough to detect. By then, it's too late to launch any kind of intercept mission with current technology. What's needed is a detection system capable of spotting these objects while they're still far from the Sun, ideally several years before their closest approach. Next-generation sky surveys like the Vera-Rubin Observatory might provide this early warning capability. With its unprecedented combination of sensitivity and sky coverage, this facility could potentially detect interstellar objects while they're still beyond the orbit of Jupiter, providing the years of advance warning needed to plan and execute intercept missions. The observatory's automated alert system could identify unusual moving objects and flag them for immediate follow-up observations. Even with advance warning, intercept missions would require international cooperation on an unprecedented scale. The technical challenges, financial costs, and time constraints involved would likely exceed what any single space agency could handle alone. Such missions would need to combine the resources and expertise of multiple countries, creating new models for international space cooperation. The spacecraft design for an interstellar intercept mission would face unique challenges. The high relative velocities involved mean that the encounter would be extremely brief, perhaps lasting only hours or even minutes. The spacecraft would need to carry instruments capable of making detailed measurements during this fleeting encounter, including spectrometers for composition analysis, cameras for imaging, and potentially sample collection systems. Sample return represents the ultimate goal for interstellar object missions, but also the greatest technical challenge. Collecting samples during a high-speed flyby would require innovative techniques, perhaps using aerogel collectors or harpoon-like systems to capture material from the object's surface or coma. Returning those samples to Earth would then require the spacecraft to slow down dramatically and execute a precise trajectory back to our planet. Alternative mission concepts focus on rendezvous rather than flyby encounters. If an intercept spacecraft could match the velocity of an interstellar object, it could study the visitor for extended periods, perhaps even landing on its surface. However, the propulsion requirements for such rendezvous missions are even more demanding than for flyby encounters, requiring breakthrough advances in propulsion technology. Distributed mission concepts offer another approach to the intercept challenge. Instead of launching a single large spacecraft, this approach would deploy multiple small probes along the predicted path of an interstellar object. Each probe would make measurements during its brief encounter, and the combined data from all probes would provide a comprehensive picture of the visitor. This approach could potentially be implemented with current technology, though it would still require the advance warning that comes from early detection. The scientific instruments needed for interstellar object encounters would need to be highly specialized for the unique conditions they would face. The extreme cold of interstellar space, the brief encounter times, and the unknown composition of the targets all present challenges for instrument design. Mass spectrometers capable of analyzing both gas and dust, cameras optimized for low-light conditions, and magnetometers to study any magnetic fields would all be essential components of such missions. Communication during intercept missions presents additional challenges. The high speeds involved and potentially large distances from Earth would test the limits of current deep space communication systems. Real-time control would be impossible during the encounter itself, requiring spacecraft to operate autonomously during the most critical phases of the mission. The potential scientific return from successful intercept missions would be transformational. Direct analysis of materials from another star system could reveal details about planetary formation processes, stellar environments, and potentially even organic chemistry that might be relevant to understanding the distribution of life throughout the galaxy. Such missions could provide ground truth for theories about planetary system evolution that are currently based entirely on observations of our own solar system. As detection capabilities improve and more interstellar objects are discovered, the pressure to develop intercept mission capabilities will likely intensify. The rare opportunities these visitors provide for studying materials from other star systems are too valuable to pass up indefinitely. While the technical challenges remain formidable, the combination of improving detection systems and advancing propulsion technologies might soon make such missions feasible. The first successful intercept of an interstellar object would mark a milestone in human exploration comparable to the first missions to other planets. It would represent our first direct contact with materials from beyond our solar system, opening a new chapter in our understanding of the galaxy we inhabit. Could life itself be catching rides between the stars on these wandering worlds? This question touches on one of the most intriguing possibilities in astrobiology, the idea that life might spread throughout the galaxy, not through deliberate exploration, but by hitching rides on the countless objects that drift between stellar systems. It's a concept that sounds like science fiction, but rests on solid scientific foundations and has been seriously considered by researchers for decades. The hypothesis, known as panspermia, suggests that life could survive the long journey through interstellar space and potentially seed new worlds when these traveling objects encounter other planetary systems. The idea isn't that complex organisms could survive such voyages, but rather that the hardiest forms of life, perhaps bacteria or even simpler organic molecules, might endure the harsh conditions of space and remain viable for millions of years. The conditions that life would face during an interstellar journey are undeniably extreme. Space is cold, with temperatures just a few degrees above absolute zero. It's also flooded with harmful radiation from cosmic rays and ultraviolet light from distant stars. There's no atmosphere to breathe, no liquid water, and essentially no energy sources that life as we know it could use. It seems like the perfect recipe for sterilization rather than preservation. Yet, life on Earth has repeatedly surprised scientists with its ability to survive in environments once thought to be completely hostile. Organisms called extremophiles have been found thriving in boiling hot springs, highly acidic pools, the depths of the ocean around volcanic vents, and even in the highly radioactive environment inside nuclear reactors. Some bacteria can enter dormant states that allow them to survive for thousands or even millions of years without nutrients or water. Laboratory experiments have shown that certain microorganisms can survive exposure to the vacuum of space for extended periods. Some bacteria and lichens have been sent to the International Space Station and exposed to the space environment for months at a time, only to be revived successfully when returned to favorable conditions on Earth. While these experiments don't replicate the million-year timescales of interstellar journeys, they demonstrate that life can be remarkably resilient. The interior of an interstellar object might provide some protection from the harshest aspects of space. While the surface would be constantly bombarded by cosmic radiation, organisms buried even a few meters below the surface would be largely shielded from this radiation. The interior would still be extremely cold, but this might actually work in favor of preservation, slowing down all biological processes to a near standstill and potentially allowing dormant organisms to survive for geological timescales. Water ice, which appears to be common in interstellar objects like 3I Atlas and Borisov, could provide additional protection and possibly even a medium for very slow biological processes. While liquid water cannot exist in the vacuum of space, localized heating from radioactive decay or other energy sources might occasionally create small pockets of liquid water within an object's interior. Such environments might allow dormant life to briefly reactivate and possibly even reproduce before returning to dormancy. The organic chemistry that astronomers have detected in some interstellar objects adds another layer of intrigue to the panspermia hypothesis. Complex organic molecules, the building blocks of life, appear to be preserved in these cosmic wanderers. While the presence of organic chemistry doesn't prove the existence of life, it demonstrates that the chemical precursors to life can survive interstellar journeys and might be distributed throughout the galaxy. Recent discoveries about Earth's own biosphere have expanded our understanding of where life might originate and survive. The deep subsurface biosphere, extending kilometers below Earth's surface, harbors vast communities of microorganisms that live completely independently of sunlight and the surface environment. If similar subsurface ecosystems exist on other worlds, they might be more likely to survive the kinds of catastrophic events that could eject chunks of their planet into interstellar space. The timing of life's emergence on Earth also provides some circumstantial support for panspermia scenarios. Life appears to have emerged on our planet relatively quickly after conditions became suitable, perhaps within a few 100 million years of Earth's formation. Some researchers argue that this rapid emergence suggests life might have arrived from elsewhere rather than originating on Earth itself, though this interpretation remains highly speculative. Mars presents a particularly intriguing case study for potential life transfer between worlds. The red planet likely had conditions suitable for life during its early history, and impacts from asteroids and comets have certainly ejected material from Mars into space. Some of this material has even reached Earth in the form of meteorites. If life ever existed on Mars, it's conceivable that some organisms might have survived the journey to Earth aboard these natural spacecraft. The discovery of complex organic molecules in meteorites, including some that appear to be of biological origin, provides additional evidence that organic material can survive interplanetary journeys. While the distances and timescales involved in interstellar panspermia are much greater than those for travel between planets in the same system, the basic principles might be similar. However, significant challenges remain for any panspermia scenario. The radiation exposure during million-year journeys through interstellar space would be cumulative and severe, potentially damaging the DNA and other essential molecules that life requires. The probability of a life-bearing object actually encountering a suitable planet around another star is vanishingly small given the vast distances and sparse distribution of stellar systems. Even if life could survive an interstellar journey and successfully reach another planetary system, it would still need to successfully land on a suitable world and find conditions amenable to growth and reproduction. The vast majority of worlds in any planetary system are likely to be unsuitable for life as we know it, being either too hot, too cold, or lacking essential resources like liquid water. Nevertheless, the sheer number of objects that appear to be wandering between stars suggests that if panspermia is possible at all, it might be happening on a galactic scale. With billions of stellar systems in our galaxy and countless small bodies being ejected from each system over cosmic time, the opportunities for life transfer, however unlikely for any individual object, might add up to significant probabilities when considered across the entire galaxy. The study of interstellar objects like 3I Atlas provides an opportunity to search for evidence of this process. Future missions that could analyze samples from these cosmic wanderers might be able to detect organic molecules or even preserved biological material that could shed light on whether life travels between the stars. Such discoveries would revolutionize our understanding of how life might spread throughout the universe. While we watch visitors from afar, our own solar system is quietly broadcasting its presence to the galaxy. Every piece of rock, ice, and dust that gets ejected from our cosmic neighborhood becomes an ambassador to the stars, carrying with it chemical signatures and potentially even biological materials that could tell distant civilizations about the world we call home. In this grand galactic exchange program, we are simultaneously receivers and senders, participants in a vast network of material transfer that connects every stellar system in the galaxy. The process that brings us visitors like 3i Atlas also operates in reverse, with our solar system contributing its own wanderers to the interstellar population. During the early, chaotic period of planetary formation, gravitational interactions between the giant planets likely ejected countless small bodies into interstellar space. Some estimates suggest that for every object remaining in our Kuiper belt, hundreds or thousands of similar objects were flung out of the solar system entirely during these early reshuffling events. These ejected objects carry with them a record of our solar system's composition and history. Like cosmic messages in bottles, they preserve samples of the materials from which Earth and the other planets formed. The ice and rock that make up these wandering ambassadors contain isotopic signatures that reflect the specific nuclear processes that occurred in the stars that preceded our Sun, as well as the particular mixture of materials that condensed in our protoplanetary disk. From the perspective of astronomers in distant star systems, objects ejected from our solar system would appear much as 3i Atlas appears to us, mysterious visitors following hyperbolic trajectories, displaying unfamiliar chemical compositions, and carrying clues about the environment in which they formed. An alien astronomer studying a piece of our Kuiper belt that wandered into their system might puzzle over its composition, just as we wonder about the origins of our interstellar visitors. The diversity of materials in our solar system means that different types of ejected objects would tell different parts of our story. Rocky asteroids from the inner solar system would carry information about the high-temperature environment close to our Sun, while icy comets from the outer regions would preserve materials that condensed in the cold outer reaches of our protoplanetary disk. Each type of ejected object would provide a different window into our solar system's formation and evolution. Earth itself contributes to this cosmic export program through impact events that can launch material into space. Large asteroid or comet impacts have certainly ejected rocks and possibly even biological material from our planet's surface. Some of this material might have enough velocity to escape the solar system entirely, carrying with it samples of Earth's geology and potentially even fossilized microorganisms or organic molecules. The possibility that Earth rocks carrying traces of life might be wandering through the galaxy adds a profound dimension to our understanding of panspermia. While we search for evidence of life arriving on ancient meteorites, we might simultaneously be seeding the galaxy with our own biological materials. Every major impact event in Earth's history might have created a shower of life-bearing projectiles that could eventually reach other star systems. The chemical evolution of our solar system over its 4.5 billion-year history means that objects ejected at different times would carry different signatures. Materials ejected during the early, violent period of planetary formation would look very different from objects ejected more recently. An interstellar archaeologist studying a collection of objects from our solar system might be able to piece together a timeline of our system's evolution. Our Sun's position in the galaxy also influences how our ejected materials spread through space. As our solar system orbits the galactic center, it travels through different regions of the galaxy with varying stellar densities and gravitational environments. Objects ejected when we were passing through a dense stellar region might be more likely to encounter other star systems than those ejected during passages through more isolated regions. The metallicity of our solar system, reflecting the abundance of elements heavier than hydrogen and helium, provides another distinctive signature that our ejected objects would carry. Our Sun is what astronomers call a population ice star, formed from material that had already been enriched by multiple generations of stellar nucleosynthesis. This gives our solar system a particular chemical fingerprint that would be recognizable to astronomers in other systems. The presence of liquid water on Earth and the complex organic chemistry associated with life might make objects ejected from our solar system particularly interesting to alien astrobiologists. If life is rare in the galaxy, samples of biological material from Earth could be extraordinarily valuable scientific specimens for civilizations that encounter them. Conversely, if life is common, our biological exports might be just another example of the organic chemistry that pervades the galaxy. The orbital dynamics that eject objects from our solar system also influence their subsequent distribution through the galaxy. Objects ejected with higher velocities are more likely to travel farther from their origin point before encountering other stellar systems. The direction of ejection, influenced by the gravitational fields of the planets and the orientation of our solar system relative to its orbital motion around the galaxy, affects where these materials end up. Modern space missions have inadvertently added human-made objects to this population of solar system exports. Several spacecraft launched by human civilization are now on trajectories that will eventually take them out of the solar system and into interstellar space. These artificial objects carry their own distinctive signatures of technological civilization, from the materials used in their construction to the information stored on golden records and plaques. The timescales involved in this galactic material exchange are staggering. Objects ejected from our solar system billions of years ago might only now be encountering other stellar systems, while materials ejected today won't reach distant stars for millions of years. This means that the interstellar objects we observe today might be samples from stellar systems as they existed in the distant past, preserving ancient chemistry and possibly even extinct biological materials. As we continue to study visitors like 3I Atlas, we're not just learning about distant stellar systems, but also gaining insight into our own cosmic context. We're part of a vast, interconnected network of material exchange that has been operating for billions of years, connecting every star system in the galaxy through the slow drift of ejected objects through interstellar space. The realization that our solar system is both a receiver and broadcaster in this galactic network adds a humbling perspective to our place in the universe. We're not isolated observers studying distant phenomena, but active participants in a cosmic conversation that spans the galaxy. Every interstellar visitor that passes through our system is potentially balanced by objects from our own system, visiting distant stars, carrying news of our existence to civilizations we may never directly contact. Tomorrow's telescopes will turn these rare cosmic encounters into a regular correspondence with the galaxy. The transformation in our ability to detect and study interstellar objects is about to accelerate dramatically, driven by new survey telescopes, improved data processing techniques, and automated detection systems that will revolutionize our understanding of the material wandering between the stars. What has been a trickle of discoveries may soon become a flood of information about the galactic neighborhood we inhabit. The Vera Rubin Observatory, set to begin operations in the coming years, represents perhaps the most significant advance in interstellar object detection capabilities. This facility will photograph the entire visible sky every few nights with unprecedented sensitivity and resolution, creating a time-lapse movie of the universe that will capture the motion of countless moving objects. Its wide field of view and rapid survey speed will make it far more likely to detect interstellar visitors while they're still far from the Sun, potentially providing the advance warning needed for detailed follow-up studies. The data volume that next-generation surveys will produce is staggering. The Rubin Observatory alone will generate about 20 terabytes of data every night, requiring sophisticated automated systems to process images, identify moving objects, and flag unusual discoveries for human attention. Machine learning algorithms trained to recognize the subtle differences between solar system objects and interstellar visitors will become essential tools for sifting through this deluge of information. These automated detection systems are already being developed and tested using data from current surveys. Advanced software can now identify potential interstellar objects within hours of their discovery, triggering immediate alerts to observatories around the world. This rapid response capability will be crucial for maximizing the scientific return from each discovery, as interstellar objects typically provide only limited windows of opportunity for detailed study. The improvement in sensitivity provided by next-generation surveys will dramatically expand the size range of detectable interstellar objects. While current surveys can reliably detect only the largest visitors, future systems may be sensitive enough to spot objects just tens of meters across. This will reveal whether the population is dominated by smaller bodies, as many theoretical models predict, or whether the large objects we've discovered so far are truly representative of the broader population. Early warning systems for potentially hazardous asteroids are also being adapted to serve as interstellar object detectors. Projects like the European Space Agency's proposed Space Situational Awareness System will monitor space around Earth for various types of objects, including potential interstellar visitors. These systems combine ground-based telescopes with space-based sensors to provide comprehensive coverage of near-Earth space. The integration of multiple survey systems around the world is creating a global network for interstellar object detection and tracking. Telescopes in different locations can observe the same objects at different times, providing continuous coverage as Earth rotates and extending the window for detailed observations. This international cooperation is essential for studying objects that may be visible from only certain locations on Earth during their brief passage through the inner solar system. Space-based telescopes offer unique advantages for interstellar object detection. Free from atmospheric interference and able to observe continuously without weather interruptions, space-based surveys can potentially detect fainter objects and track them for longer periods. The James Webb Space Telescope and other advanced space observatories can provide detailed spectroscopic analysis of interstellar visitors, revealing composition details that are difficult or impossible to obtain from ground-based observations. The coordination of follow-up observations is becoming increasingly sophisticated as the astronomical community learns from experience with previous interstellar discoveries. Protocols are being developed to ensure that when a new interstellar object is discovered, telescopes around the world can quickly focus their attention on the visitor, maximizing the scientific information gathered during the limited time it remains visible. Artificial intelligence and machine learning are revolutionizing not just the detection of interstellar objects, but also the analysis of the data they provide. Advanced algorithms can automatically classify objects based on their spectroscopic signatures, identify unusual compositions or behaviors, and even predict optimal times for follow-up observations. These tools will become increasingly important as the discovery rate accelerates beyond what human astronomers could handle manually. The possibility of discovering multiple interstellar objects simultaneously will require new approaches to observation scheduling and data analysis. If future surveys detect dozens or hundreds of these visitors each year, astronomers will need to develop triage systems to prioritize which objects receive detailed study based on their scientific interest and observability. Real-time alert systems are being developed to ensure that significant discoveries reach the global astronomical community within minutes of detection. These systems will automatically analyze new observations, identify potentially interstellar objects, and distribute alerts to observatories, research institutions, and even amateur astronomers who might contribute to follow-up observations. The democratization of astronomy through improved technology and data sharing is expanding the pool of potential discoverers. Advanced amateur astronomers equipped with high-quality cameras and automated telescopes are already contributing to interstellar object discoveries, and this trend is likely to accelerate as technology becomes more accessible and affordable. Citizen science projects are being developed to harness the pattern recognition abilities of volunteers in identifying unusual objects in survey data. While automated systems excel at finding obvious moving objects, human eyes are often better at spotting subtle anomalies or objects that don't fit standard patterns. Large-scale citizen science projects could significantly expand our ability to find rare and unusual interstellar visitors. The statistical analysis of large samples of interstellar objects will revolutionize our understanding of these cosmic wanderers. Instead of studying individual objects one at a time, astronomers will be able to analyze the properties of hundreds or thousands of interstellar visitors, revealing population characteristics, composition trends, and evolution patterns that are invisible when studying just a few examples. Predictive models are being developed to forecast when and where interstellar objects might be discovered. By analyzing the orbits and approach directions of known objects, combined with models of galactic dynamics and stellar motions, astronomers hope to identify regions of sky that are more likely to yield discoveries. This could help focus survey efforts and improve detection efficiency. The integration of interstellar object discoveries with broader astronomical surveys will provide additional context for understanding these visitors. Projects that monitor stellar variability, search for exoplanets, or map the galactic structure will inevitably encounter interstellar objects in their data, adding to the discovery rate and providing different perspectives on the same phenomena. As the discovery rate increases, the challenge will shift from finding interstellar objects to understanding what the growing population tells us about the galaxy we inhabit. The coming decade may see the transition from individual case studies to statistical analyses that reveal the true nature and origin of the vast population of objects that wander eternally between the stars. Every interstellar visitor reminds us that our solar system isn't an island, but part of an ancient cosmic archipelago. The discovery of objects like 3I Atlas has fundamentally changed how we see ourselves in the universe, transforming our perspective from that of isolated observers to active participants in a vast galactic ecosystem. We're beginning to understand that stellar systems throughout the galaxy are connected by invisible highways of ejected material, creating a network of communication that has been operating for billions of years. This new perspective represents a profound shift in our cosmic worldview. For most of human history, we've thought of space as empty, with isolated islands of matter orbiting distant stars in perfect isolation. The discovery of interstellar objects reveals that space isn't empty at all, but filled with travelers carrying news from distant stellar systems. Every piece of rock and ice drifting between the stars represents a connection, a thread in the vast web that links every planetary system in the galaxy. The chemical diversity we've observed in just 3 interstellar visitors hints at the extraordinary variety of environments that exist around other stars. Each object carries a unique signature that reflects the conditions in its birth system, the temperature at which it formed, the chemical composition of its parent star, the dynamics of planetary formation, and the violent events that eventually ejected it into space. These cosmic messengers are providing our first direct samples of materials from stellar environments that might be completely unlike anything in our solar system. The realization that we're part of this galactic exchange program adds a new dimension to our understanding of planetary formation and evolution. The materials that formed Earth and the other planets didn't originate in isolation, but were part of a vast recycling process that has been operating throughout the galaxy's history. Heavy elements forged in the nuclear furnaces of ancient stars, scattered by supernova explosions, and incorporated into new generations of stellar systems, create a shared heritage that connects every world to every other. This perspective has profound implications for our understanding of life's potential distribution throughout the galaxy. If interstellar objects can carry organic molecules and potentially even living organisms between stellar systems, then life itself might be part of this galactic circulation pattern. The boundaries between stellar systems become less absolute when we consider the possibility that biological material might regularly travel between them on these wandering worlds. The discovery of interstellar objects also provides a new tool for studying the evolution of planetary systems. By analyzing the composition and structure of ejected materials, we can learn about the processes that shaped other stellar systems during different phases of their development. Objects ejected early in a system's history might preserve primitive materials from the original protoplanetary disk, while those ejected later might show evidence of planetary processing and chemical evolution. The statistical analysis of interstellar object populations, as more examples are discovered, will reveal patterns that illuminate the broader processes operating throughout the galaxy. The size, distribution, composition range, and velocity characteristics of these wanderers will provide insights into the efficiency of planetary formation, the frequency of violent gravitational events, and the typical architectures of stellar systems across different types of stars. Our growing understanding of interstellar objects is also changing how we think about the search for extraterrestrial intelligence. If technological civilizations exist elsewhere in the galaxy, they might also be studying interstellar visitors, perhaps even launching their own missions to intercept and study these cosmic travelers. The network of material exchange that connects stellar systems might also serve as a communication network, carrying not just chemical information, but potentially even deliberate messages between civilizations. The development of technologies to study and potentially intercept interstellar objects represents a new frontier in space exploration. Future missions that successfully rendezvous with these visitors will mark humanity's first direct contact with materials from beyond our solar system, expanding our presence beyond the gravitational influence of our Sun. Such missions would represent a new form of exploration, one that brings distant worlds to us rather than requiring us to travel to them. The international cooperation required to study interstellar objects effectively is fostering new models of scientific collaboration. These rare visitors don't respect national boundaries or institutional affiliations, and studying them requires rapid coordination between observatories, research institutions, and space agencies around the world. The protocols being developed for interstellar object discoveries may serve as templates for international cooperation in other areas of space science. The philosophical implications of our connection to the galactic community are equally profound. We're not the products of an isolated stellar system, but participants in a cosmic ecosystem that has been exchanging materials for billions of years. The atoms in our bodies were forged in ancient stars, and may have traveled through interstellar space multiple times before eventually becoming part of Earth. In a very real sense, we are already citizens of the galaxy. This cosmic perspective also highlights the responsibility that comes with our growing technological capabilities. As we develop the ability to study and potentially alter the trajectories of interstellar objects, we become active participants in the galactic material exchange rather than passive recipients. Our decisions about how to interact with these visitors could have consequences that ripple throughout the galaxy over cosmic timescales. The study of interstellar objects is revealing that the galaxy operates as a vast, interconnected system where matter, energy, and potentially even information flow between stellar systems over cosmic timescales. We're beginning to see patterns and connections that were invisible when we focused only on individual stars and planets in isolation. This systems-level view of the galaxy represents a new frontier in astronomy, one that may be as transformative as the discovery of exoplanets was for our understanding of planetary systems. As we continue to discover and study visitors like 3I Atlas, we're not just learning about exotic objects from distant star systems, but also gaining insight into our own cosmic heritage. Every interstellar object tells part of the story of how stellar systems form, evolve, and interact with each other across the vast scales of space and time. These wandering worlds are teaching us that we live not in an isolated solar system, but in a galaxy where every star is connected to every other through the patient drift of material across the cosmic dark. The future holds the promise of regular communication with our galactic neighbors through the medium of interstellar objects. As our detection capabilities improve and our understanding deepens, these cosmic messengers will become familiar visitors rather than rare surprises. We're entering an era where the study of interstellar objects will provide a constant stream of information about stellar systems throughout our region of the galaxy, creating a new form of astronomy that explores distant worlds by studying the travelers they send our way. In this grand cosmic perspective, 3I Atlas represents more than just a remarkable discovery. It's a reminder that we're part of something much larger than ourselves, connected to the entire galaxy through ancient processes that have been operating since the first stars began to shine. Every interstellar visitor is an invitation to expand our understanding of our place in the universe and our connection to the vast cosmic community that surrounds us. And so, we arrive at the end of our gentle journey through the cosmos, following one remarkable visitor as it glides past our sun and back into the darkness between stars. Comet 3I Atlas will continue its ancient voyage, carrying with it our observations and questions, perhaps toward another star system where curious beings might wonder about the traveler that once visited a small blue world. We've wandered from that July night in Chile through the mathematics of hyperbolic orbits, from spectroscopic analysis to dreams of future missions. We've seen how 3 small visitors have opened our eyes to a galaxy filled with wandering worlds, each carrying stories from distant suns. And we've glimpsed our own solar system not as a lonely outpost, but as one voice in a vast cosmic conversation that's been going on for billions of years. Tonight, as you settle into sleep, perhaps you'll carry with you the quiet wonder of knowing that somewhere in the darkness above, ancient travelers are passing by, bearing witness to the endless dance of gravity and time that connects every star to every other. The universe is vast, but these visiting messengers remind us that we're all part of the same magnificent, interconnected story. Thanks for joining us here at Sleep Science. Sleep well and dream of distant stars.